Hello, my name is Dana. I am an undergraduate research assistant at the Institute of Smart Systems and Artificial Intelligence. This is the first part of the tutorial aimed to introduce you to face detection in computer vision. In this part, we will cover basics of face detection and proceed to a coding example in Python. Let us define face detection first. According to the formal definition, it is a machine learning-based computer vision technology used for detecting faces in digital images. The applications of the technology include various fields such as biometrics, security, law enforcement, personal safety, and tracking in real time. It helps to identify which parts of the video or image should be focused on, which is the first step for key applications including face tracking, face recognition, and face analysis. There are various methods for detecting faces, and the pipeline differs depending on the approach being used. Here you can see the general face detection pipeline, which is very straightforward. The algorithm identifies the region with the face and delimits the corresponding region with a rectangular frame, which is called the bounding box. Even though face detection has progressed over the last few years, there are still some challenges and promising research directions for future advancements. For instance, pose variation, face occlusion, and illumination problems are some of the most critical challenges for face detection, since factors such as accessories, medical masks, and even slight changes in the lighting conditions put huge constraints for the algorithm. Although advanced deep learning algorithms can handle such cases, it is still a challenging task. Such problems can be solved by developing new large-scale datasets of faces in an unconstrained environment, so-called faces in the wild datasets. When it comes to the robust detection of tiny faces, several works have been already focused for detecting faces that appear in tiny regions in images. However, there is still much room for improving the accuracy of these models for the more challenging cases of tiny faces with heavy occlusion. Interestingly, the bias reduction issue, or accuracy disparity across demographic groups, is gaining popularity currently. Researchers are actively engaged on this topic for face recognition, but no work is found on possible bias in face detection. Here is a list of the most widely used face detection datasets in recent literature. All datasets contain annotations. It is important to mention that wider face, labeled faces in the wild, unconstrained face detection datasets are very challenging datasets that have a wide range of difficult elements, including occlusions, different poses, and low resolution. Whereas multi-attribute labeled faces dataset is the first face detection dataset that supports fine-grained evaluation and, along with bounding boxes, contain annotations of other facial attributes such as gender and some facial deformations. Now let's move on to discussing the most common methods that are used for face detection. These are machine learning and deep learning based methods. Early face detection efforts were mainly based on the machine learning approach, in which handcrafted features were extracted from the image and then fed into a classifier to determine face regions. We can mention HAR cascade classifier, histogram of oriented gradients followed by support vector machine. In this case, these works are considered classical approaches and state-of-the-art at their time. However, face detection accuracy was still limited in challenging images with multiple variation factors that we discussed earlier. The great advancement of deep learning in the past 6-7 years opened the door for promising and breakthrough model architectures. Among the recent ones, we could mention RCNN-based architectures, feature pyramid network models, and single-shot detector models. In this tutorial, we will learn how to detect faces using the models offered in DLEAP library. DLEAP offers two different functions for face capture, which represent two approaches that we have covered in the previous slide. These are histogram of oriented gradients followed by linear SVM and CNN. If we compare these two models, histogram of oriented gradients followed by linear SVM uses lower resources, efficiently operates on CPU, and has relatively low impact model requirements. However, it has low occlusion handling and can overcrop some facial features. In contrast, CNN can recognize difficult face orientations. It is extremely fast when operating on GPU, and it has lightweight training architecture. However, CNN can produce bounding boxes even more restricted than Hawk and performs much slower on CPU. Both models share the inability to detect smaller faces than 80 pixels square and require custom builds for some specific cases. To summarize this slide, the two models have different visual results and inference speed. Now let's see the differences in practice. Now let's look at the code itself. The file is called facedetection.py. When you open it, you can see that only 4 libraries are used to conduct this experiment and the code is straightforward. Face recognition provides Python API for the lips face detection, recognition, and landmark prediction model. We will use it for face detection. For more information, you can visit their GitHub page that will appear right here. Argparse is needed for implementing a user-friendly command line interface. Time is used to record time taken for detecting faces in one image. And finally, we use OpenCV to read the images, to visualize the detected bounding boxes, and to show the result. To test the models, you will need to provide 3 arguments, which are the path to the image and upsample. This is how many times your model needs to upsample the image while looking for faces. Higher upsample values help to detect smaller faces. In this case, the default value was set to 1. And finally, you will need to provide the model itself. This is Hawk or CNN. The algorithm is as follows. Firstly, it reads the image, then calls face location function from face recognition library, providing the correct arguments, and finally it saves the coordinates to the list and then records time. And in this block, we are using the OpenCV function rectangle in order to visualize these coordinates on the image in the correct format: start X, start Y, and X and Y. Finally, again, using OpenCV, we just show the result. Now let's test the models. For that, we will use 2 images, which is example 1, example 2. Example 1 corresponds to the easy image, and example 2 will provide harder case for our models. Here I have already prepared the line for calling our function, and we provide the argument. Firstly, we will start from example 1, which is easy image. Then we'll provide the default value for upsample, which is 1, and we will start from Hawk. Now let's press enter. As you can see, all faces here are detected and the detections are pretty accurate. The inference time is about 0.5 seconds, which is impressive. Now let's try another image, which is harder one. We will just change the image to example 2. Press enter. As you can see, 3 faces are not detected. Let's try another upsample value and see what will change. For that, let's change upsample 1 to 2 and press enter again. As you can see, now the situation is better because only 1 face is not detected in comparison to 3 in the previous trial. You may notice that in all 3 cases the inference time is pretty high, which means that the Hawk model is really fast. Now let's move on to CNN. For that, let's firstly use the easier example and just change the model to CNN. Press enter. And this might take more time, so you need to wait. Now here is the result, and as you can see, all faces are detected and the detections are pretty accurate, but the inference speed is about 20 seconds, which is a lot more than for Hawk. Now let's try the harder example for CNN. For that, let's use the same upsample value as we did in the Hawk, which is upsample 2 for harder case. Just change the image to example 2. Press enter, and again you will need to wait. The process took even longer time. The inference time is about 33 seconds, but according to the results, all faces are detected with upsample value 2, as compared to Hawk, because with Hawk, one face was not detected. So we have just seen the difference between these two models in practice. Hawk works much faster but detects faces less accurately than CNN on challenging images. You can try this tutorial yourself. Thank you very much for watching.